Before we start, let me please introduce our presenter today. It's Florian Knigge. Florian is our technical leader for metrology, who holds a master's degree in electrical engineering and has 10 years of experience in X-ray and CT with the main focus of metrology. In his daily work, Florian Knigge supports metrology customers as well as our global sales team. He was one of our main developers for our first metrology specified CT scanners and has since then become our technical leader in the field of metrology. Let me also introduce Hans-Uwe Matzen, our senior sales consultant. He has an extended experience of more than 40 years with the company within the X-ray technologies business. He has held various roles in engineering, service, product and project management and sales. Florian will in the next minutes start with his presentation, and Hans-Uwe will support during a Q&A session at the end of this presentation for potential questions or inquiries which you might have. You can either submit your questions at the end, during the session via the chat window within this Windows Teams software, or you wait until the end of the presentation where you can verbally ask your questions and get directly the answers. During the presentation, we would like to ask everyone to mute your microphones. Last but not least, we would also like to inform you that we will record this session and will make it available in the internet at our YouTube channel in the following days. Yeah, I think all is said. With all this, I would like to now pass it on to Florian. I think you are already start sharing your presentation. It's now yours.
Okay, thank you very much for the introduction. I hope everybody can hear me well. Jan, can you confirm?
Yes, I can confirm.
Okay, perfect. Thank you very much. So yeah, also from my side, thank you very much for joining this second webinar of this series, this virtual control show. As Jan mentioned, we will be covering the CT metrology, but before we start with that, just a few more additions to what Jan already said. So we will be able to host individual demonstration sessions as well. So if you, after this presentation, want to know more about metrology by CT, if you're curious to see how this works on your particular part, on your particular application, feel free to contact us afterwards. We will be able to do a demonstration session, either web-based through cameras, or even face-to-face. So all our customer solution centers worldwide, they are open, they are operational. Of course, we make sure that we comply with all the standards regarding hygiene and safety in these difficult situations. But again, feel free to contact us if you are interested in a particular individual demonstration. We will have some more webinars in the next weeks. We will have some podcasts, so stay tuned on the channels we have, like LinkedIn, Waygate, our newsletter, and so keep an eye out for that as well. So now, without further ado, let's start with my presentation today. As mentioned, the topic will be metrology by CT. So I will be covering roughly 3 topics. The first one will be CT metrology applications. So what is it good for? Where can I use it? And what is the main applications that we see? What are customers doing with these kind of CT systems? The second thing will be the metrology background. So I will give you a little bit of background information on what I think is important to understand when it comes to metrology. What are the key takeaways for the metrology field? And then last but not least, I will talk about our technical solutions, so Waygate Technologies technical solutions. What did we come up with? How do our systems perform regarding metrology, and how do we make sure that they perform in a way that we want them to? So first of all, let's talk about CT metrology applications. For those of you, hopefully a lot of you joined the session yesterday by our product manager, Oliver Brunke. He gave a very good detailed overview of where is our technology used? What is the benefit of it? So I will not go into too much detail. I don't want to cover everything that we have been covering yesterday as well. Just a few keywords here on this first slide. So basically, CT metrology is everywhere where CT is. So there's an application pretty much in every industry that uses CT at the moment, also for CT metrology. So that covers aviation, automotive, electronics, and everything else you can see on the left-hand side. Very interesting and very new technology, of course, is the additive manufacturing, also 3D printing, where we have, by the means of this technology, we get very complex parts with maybe hidden structures on the inside. And nowadays, CT is in many cases the only way of doing measurements of these parts without destroying them, because you cannot reach it with a conventional probe or with a conventional optical scanner. So again, CT metrology is everywhere where there's metrology and where there's CT. So pretty much all over the industry. And where in this industries, on the right-hand side, you can see in which area it is. So it's pretty much everywhere. So starting in research and development in the very early product phase, for tool corrections, for example, if you set up a production process optimization, post-process controls, so pretty much all along the way. So it's really an technology that covers it all. So if you think about your company, if you think about where do we use metrology, what do we do? Do we use optical scanners, CMMs? Think about that, and think about after this presentation, maybe we benefit from using a CT, either because we have a higher throughput, or we're able to measure things that we were not able to measure before. But hopefully by the end of this presentation, you have a better idea of what this technology is capable of and where you, in your particular case, can use it. So what I want to do now is I want to just give you a very rough overview, a very quick overview of how do we work with CT data when it comes to metrology. And one of the things that we always do first when we have a new customer, then when we want to show what metrology actually is capable of, is we do a nominal actual comparison. So if you have a part designed in your engineering department, you have some sort of CAD model of it, or some sort of STL, or even golden sample that you scanned before. So some sort of reference maybe. This is what it's supposed to be. So you have all the ideal geometry, you have all the ideal distances between every point. So everything here in this case is ideal. For example, a step file or something like that. On the other hand, of course, you have a CT scanner. I will not be covering the whole details of how CT scans work, but basically what you get in the end is you get a full 3D representation of your part. So here you can see this one out here is a real life part, a 3D representation, fully 3D model of the surface of this part. So this is an aluminum casting part. And of course, as we all know, nothing is perfect in the real world. So this manufactured part, and also this model here has its deviations from the ideal CAD model. So you have tolerances by the way you manufacture it, by the way maybe your suppliers deliver the parts. So there's tolerances in that. And what we want to do first is, of course, the main goal of metrology always is to see how big is the difference between the nominal and the actual part. And a very quick and easy way that you can do with CT is you can do a nominal actual comparison color coded. So what you can do is you take your CAD on the left hand side, or your model of your part. You take your actual part that you scanned in our CT scanner. Depending on what configurations you choose, it might be a minute scan or an hour scan. Really, there's a lot of flexibility in there. You can do very quick scans, you can do very detailed scans that take longer, and then you combine those two. And you see here, in the middle here, you see a color-coded a color map of this deviation. So, for example, what we can see here is on the so green, just like a traffic light, green means go, green means everything is good. So for example, at this plane here, down here, and here, this is everything is nice and green. So that means there's no deviation between the actual part and the nominal part. The reason for that is because this is the plane I aligned it with. We have to do some alignment. So this is my alignment plane, and of course the alignment is always perfect. But what you can see, for example, on top here, this deep purple lines or surfaces here, they have a high deviation. That means you can see here it's minus 0.3 or bigger. So that means that this is much, much lower than we want it to be in our model. So for example, you can see there's a deviation here. Without doing Could you please go on mute? That would be very, very helpful.
Эталонно идет дальше сравнение.
Okay, thank you. So sorry. So yeah, we can see it in this. Go one back. So we can go the purple one here means that we have high deviations between the nominal and the actual object, or even here we have slighter small deviations, but still deviations. So you can see with just one glimpse, it's basically just one or two clicks in the software we're using here. In this case, it's Volume Graphics. You have the CT scan, you combine it with your CAD model, and just like that, you have a knowledge about where are the issues in my part. Of course, what you can also do is you can not only use the comparison between a CT scan and a nominal part like a CAD model, you can also compare one CT scan with another CT scanner. So on the left-hand side here, you could also have another CT scan that you maybe done 2 weeks ago. So what we've seen customer doing is they take a CT scan before they deliver a part to a customer. Then the customer gets the part, he uses it, and at some point there's a failure. They send back the part, they do another scan, and they compare these results. Because we're doing a CT scan and because we're having a full 3D representation, we're able to do comparisons with of different times of the existence of this part afterwards. So there's a lot you can do with this very simple nominal actual comparison. You can see actually a lot of things going on in your part. So for example, where there's a wear off, stuff like that. And of course, if you think more about a traditional metrology approach, if you think about a CMM or an optical scanner, typically what you do is you create so-called GD&T, geometric dimensioning and tolerancing. So you create some sort of objects, cylinders, planes, cones, here seen on the left-hand side. And then you give them some measurements, for example, perpendicularity of a certain axis regarding a certain datum element A, parallelism between two planes here, or flatness of a plane. And what you can see here is on the left-hand side is this is our CAD model. So what we did here in this case is we created our measurements on our model itself. So we didn't even need to do a scan before we created our measurements. So because everything is digital after we do the CT scan, we have a full representation of the CT of the part in our computer. Basically, we can then later on just copy and paste. So we create all the measurements here before we even started the first scan, maybe even during construction of the part itself, the so-called PMI data. So we can actually, while we are designing the part, we can actually take care of the measurements that we later on want to do in our quality control. And then once we've done the CT scan, it's basically just what you know from Microsoft Word or Microsoft Excel. It's just Control-C, Control-V, so copy and paste. So you copy and paste your measurements that you created beforehand, you paste them on your actual CT part here on the left-hand side, and you can see the fit points here color-coded now again. So this every green dot that you can see on the screen is a fit point that we created to afterwards create from this fit points our geometry elements. And you can see now here that there's deviation. So again, it's color-coded. Red means higher deviation from the actual cone or cylinder. So here you can see this is a real-life part. So of course, it's not perfect. So then you can see on the right-hand side our measurements, our features. So for example, you can see the flatness here. In this case, it's red. That means it has a deviation, or the flatness is bigger than 0.2 millimeters, for example. So what you can do is you can create your measurements beforehand, and then you can just transfer them to your CT part. This is especially interesting if you talk about automation. If you have not one part, but a million parts, or let's say 1,000 parts, you don't want to create your measurements over and over again by hand. You create them once, and then it's just a script or batch, as we call it, and it just runs automatically without you even touching the system, and you get report after report after report. Of course, if you're working more in an engineering side of things, not in production, or if you want to do reverse engineering, you can do that as well. So you can do you don't have a CAD model, you just do your CT scan and you create your objects directly on the CT surface. This is of course also possible. And one more nice thing about this is because we have all the CT data available, it's just a matter of seconds. So it doesn't really make a difference in computing time, or not much, whether you do one measurement or 100 measurements. Whereas for example, with a CMM, with a coordinate measurement machine, the tactile measurement, you have to probe each and every point individually. So it takes a while to get 100 measurements, whereas here it's one CT scan, no matter if you want to do one measurement or 100. That's a very, very nice feature if you think about throughput, if you think about time. And of course, because it is all digital, because it's all just the 3D representation inside your computer, and meaning a full 3D representation without any gaps in between, we are able to do all the analysis that we know from the CT metrology side. So we've seen 2 of them. It's the GD&T and the color-coded normal action comparison. We can actually compare this into one analysis. And because we're working here with a CT scanner that has a very good image quality, we can also see gray value information. This is still there. Here on the on the metrology side of things, we only work on surface information. So we only take into account the surface of the object that we determined beforehand and say, well, from this surface to this surface, there's a certain measurement, right? But on the left-hand side, on the right-hand side here, you can see there's much more information in this scan. Inside the part, there is, for example, a lot of porosity. You can see it here. These dark areas here. This is porosity. There's air inclusions in this aluminum casting. Same on the other side. And now, if you want to, you can say, well, I did my CT scan, and my goal was to do maybe normal X-ray comparison or some sort of metrology. But because I already have the data, why not use it? Why not also have a look at the porosity and maybe determine whether or not the porosity is too close to the wall or it is too big or too small? So you can combine the metrology side of things with a more traditional analytical side of CT, and therefore all this with just one scan. So it's no extra time doing an extra analysis, at least not on the acquisition side, because once we have the 3D model, you can use it. So this is just a quick or rough overview of what is possible when it comes to applications. So these are the main applications that I see in metrology. Of course, there's always some special things going on. And as I mentioned quickly before, we are, in this case, for these demos, we were using volume graphics software. It's called VG Studio Max. We see ourselves at the manufacturer of CT systems and as delivering high quality, high accuracy CT scans. Whether or not you are using software like Volume Graphics, VG Studio afterwards for your evaluations, or maybe something like Aviso or Polyworks, we are open to it. We have an open file format, so you can take our CT scan and use it in whatever software you like. We have some, for example, some university customers, they have PhD students writing their own software. That's fine for us. We deliver high accuracy CT scans. What you do with that in the end, we give you the support you need, but you are free in choosing your own software product in the end. So that was now the more application side of things. So what do we do with a CT scanner metrology? How do we do measurements on that? Now I want to talk a little bit about background. And normally I give a 4 to 5 day course, classroom course on CT metrology. Now we're trying to do that in 10 minutes. So of course, it's a very high level overview. We will not go into too much details. I just want to give you what I think are the key points regarding this metrology, let's say theory, let's call it. So, and if we talk about things, I always like to define what we're talking about. So what is metrology? And if you just go on Google or on Wikipedia, there's different definitions by different organizations. And one of the things that's one of my colleagues found that, I mean, I like it a lot, is by the BIPM. And it says, what is metrology? Metrology is the science of measurement, embracing both experimental and theoretical determinations at any level of uncertainty in any field of science and technology. And important here in green is at any level of uncertainty. So in my own words, that means the CT metrology or metrology in general, we're not talking about CT, we're talking about metrology in general. It's not about being very accurate. It is about knowing how accurate you are. So a CT scanner, a CT metrology scanner does not have to be very, very accurate. If you buy a CT metrology scanner, that does not imply that it is the highest accuracy that you can get. It just implies that we know the system's behavior and we have the means to make sure that it's always performing in the same way. So it's reproducible and repeatable. So if you think about that more in a general approach, everything that you measure is kind of metrology. So if you use your, let's say, your meter stick, if you are working with wood and you want to build, let's say, a table, for example, you use your meter stick to create the 4 legs of your table to make sure that they all have the same size or the same length. So this is metrology. It's not very accurate. It's not up to a few microns, but it's accurate enough for this application. And the same goes for CT. So you want to make sure you don't need the highest accuracy. You need the accuracy that is good enough for your application. That is something I think is very, very important. So a little bit more on that. For example, this is all metrology equipment. Like on the left-hand side, you have a caliper that maybe many of you already used in the past. So it is, of course, not as precise as a coordinate measurement machine or an optical scanner, but is in many cases, it's accurate enough, and that's all we need. And so it's really, you have to find the right equipment for your application. And now in this, so this is all technology that's been around for quite a while, especially the caliper, of course. Also, the CMM machines have been around for tenth of years. Optical scanners as well. And now CT machines have been kind of rising. CT metrology machines have been kind of popping up everywhere. And it's still a very new technology. And I spend a lot of my time explaining to people how this technology works and to build trust in this technology. Because if you've been using a coordinate measurement machine for, let's say, 20, 30, or 40 years in your career, and now it's me coming and saying, well, we have a new technology and it can do the same. Of course, you're skeptical. And so one of the things that I want to show on the next slide is how do you approach this skepticism with the CT technology. So just one example here. Normally what happens is if you decide to maybe investigate whether or not you need a CT scanner for your application, you might just have a part that you already measured with a CMM machine. You send it to us, to our customer solution center, or you maybe arrange a visit, bring your part. We do a CT scan of this part, and then we do a measurement, and then we compare the results. And in the end, you will see, well, we did a measurement on the CMM machine, and we did a measurement on the CT machine, and they're not the same. And then there's always the question, which one is right? And what we have to understand is that we're comparing different technologies. Of course, the goal is to make them comparable, and there are ways of doing that. And there's guidelines out there. There's a VDI guideline from the German VDI organization. They're working on an ISO and on an ACM standard as well. But just on a very high level, we have to understand that there are different approaches when it comes to CMM compared to CT, for example. And of course, with other technology like optical scanners as well. So let's, for this little experiment here, say we want to measure this hole here from top to bottom. This is a cylindric hole, like a drilling. And there's another one a little bit hard to see in the back. It's just like half the way here. So typically what you would do if I gave this to somebody operating a CMM system, telling him, well, what's the diameter of this cylinder? That's my question. What's the diameter of this cylinder? He would probably, if he's experienced, he would just start. If he's not as experienced, he would probably open a book on CMM technology, and he would find, well, what defines a cylinder? And then he would say, well, we measure a circle on top and a circle on the bottom, and then we will fit the cylinder into these points, and this gives us our diameter of our cylinder. And let's say we take 8 points on top, 8 points on the bottom, for example, giving you 16 measurement points. Same for the other cylinder. With a CT, we have, as I said before, we have all the information. We have a full 3D representation of our part. So we have, to simplify it, we have the information of the whole hole. We have the surface from top to bottom, whereas with a CMM, you have to take each point individually. We already have all the information. So what we can do then is we can say, well, if I have all the information, the whole surface information, why not distribute the points evenly across the whole surface, for example? So I'll say, well, I give it, and this is just one mouse click basically. So say, well, we just want to take 10,000 points or even more on the surface from top to bottom. Same for the other cylinder. And you can see already, well, it's not the same approach, is it? So, and for this, let's call it a thought experiment. Let's say that's a cut through our hole. Of course, highly exaggerated, but let's assume that it has this kind of hourglass shape for some reason. And now we're doing our approach. On the left-hand side, we're doing our CMM approach, and on the right-hand side, we're doing our CT approach, right? So, so what do? We on the CMM, we're using 1, 2 points, and of course it goes 3D, so around a circle of like 8 or 12 points. Same on the bottom. And with a CT, we are distributing these points from top to bottom or everywhere, 10,000 or even more points all around all across the surface. And again, it's a 2D cut through a 3D hole, right? So what do we do next? Well, depending on the software we're using or depending on the configuration, we're doing some sort of fitting. So we're doing maybe Gauss fit, or we're doing a Chebyshev fit, depending on what's the purpose of this measurement. But let's assume the easiest way, we use the Gauss fit. So we take all the measurement points that we just created with our CMM or our CT, and then we're doing the least square error fitting. So we're doing a Gauss fit of a Gauss cylinder into this. And now we're measuring the diameter. And so we have the diameter of the cylinder here, telling you, well, the cylinder is, I don't know, 10 millimeters. And the CT result will be, well, it is actually 9.95 millimeters. And now I'm asking the question to myself and to everybody, what is right? And the answer is, my answer is, none of them is. So it's just the question of what do we want to achieve? So we have to think more about what the actual goal of the measurement. Maybe later on, we want to fit some rod into this. So we have to make sure that we actually measure this the smallest diameter along the cylinder. Otherwise, we say, well, it's big enough, but it will get stuck at this point somewhere. So just keep that in mind if you talk about CT and comparing CT and CMM, that you have to always ask yourself, is it really comparable? Are we comparing apples and oranges, or is it really oranges and oranges? And of course, if you want, we can say, well, if you want to compare actually to your CMM result, we can distribute the points in a way that you do it with the CMM. So we could, on the surface, just take 8 points up and 8 points on the bottom. That is possible. But then I ask you the question, why do you want to use CT if you want to just reproduce what you're doing with the CMM? You're wasting a lot of information that you have now available that you hadn't before. So why just simulate the CMM if you can go the next step? But again, this is just a very high level, and there's a lot more detail to that. And if you are curious, reach out to us afterwards, and we can have a lot more discussions on that. And we can scan your parts, and we can show you on your real life parts what it is all about and why do we think that in your case the CT is a better approach. Okay. So 1 or 2 more slides on the metrology background. This is now more for the CT background, and then we will start with our technical solutions. So one thing that I want to explain really quickly, because it's very important to understand why we're doing what we're doing with our machines, is the concept of optical magnification. So our CT scanners and pretty much every CT scanner on the market is using optical magnification. So that means that somewhere on the left-hand side, we have our X-ray source. It is our X-ray tube built by ourselves. And it's just, in this case, it's the focal spot. This is the virtual point where the X-ray is emitted. Then we have our object here. So it's your part, your customer part that you want to scan. And then we have, in this case, a flat panel detector on the right-hand side. And you can see now, I think it's in Germany, it's I think 7th or 8th grade math. So it's I think the crossing of parallel lines, something like that in English. So if you move this line now, or this object closer to your source, your image will get bigger. And if you move this object here further to the right, so closer to the detector, it will get smaller. The image on the detector will be smaller. It's the same principle as if you take your hand and you put it in front of a projector, then your shadow on the screen will be bigger if you're closer to the detector, or smaller if you go closer to the screen. So that's why it's more annoying if people in the back of the cinema get up than in the front of the cinema, because they will cover more from the movie you're watching. So closer to the tube means bigger image. And in the formula, that means magnification, M, is the FDD, that's the distance between focus and detector, focus detector distance, FDD, divided by FOD, focus object distance. right? So magnification is focus detector distance divided by focus object distance. For example, if this is exactly half the way, it would be 2 divided by 1. So that would be magnification of 2, just as an easy example. And then there's one more thing that we need. It's the so-called voxel size. So each detector has a pixel size. So each detector consists of a number of pixels, for example, 2000 by 2000 pixels. And each of these pixels has a certain distance to its neighbor, the pixel pitch, delta p in this side, or pixel size. And if you divide the pixel size by the magnification, you get the voxel size. So what's the voxel size? As I said before, we have a 3D representation of our part in our software after we do the acquisition and the reconstruction. And so this CT volume consists of many, many little cubes called voxels. And each of these little cubes has information, a gray value information regarding the, let's say, the density of the part. So if it's higher, if it's a higher gray value, it's more dense. So for example, here it's more whitish. That means there might be some high dense material, some steel, and here it's black. So that might be air or some plastic, right? Just in this example here. So, and this is like the smallest size of information we have. And now the size of this voxel, of this little cube, that's what we call the voxel size. And so if you go closer to your tube or further away from your detector, you increase your magnification, right? Going one step back, you go closer to the tube, you increase your magnification, and by that you reduce your voxel size. So your voxels will get smaller and smaller. So meaning that you have a much higher, the closer you go to the tube, the higher your resolution. And now, why am I telling you that? This is all we have when it comes to metrology. In the end, what we want to do here is we want to do measurements on our CT volume. So we want to, for example, know the distance between the steel and this plastic, for example. Maybe there's some plastic here, some air, and some steel, and we want to know the distance. So the only scale that we have is the voxel size. So we have to make very, very sure that we know the voxel size as precise as possible. And if I'm talking about precise, it's less than a micron of accuracy that we need for the voxel size, because it adds up. If you have 2000 or even 4000 by 4000 voxels, if each and every voxel has just a nanometer, let's say, deviation, then if you go across 4000 voxels, that's 4 micrometers. So it really adds up. So we have to make very, very sure that we know the voxel size and therefore the scale of the system.
Florian, you have roughly 15 minutes, 20 minutes left, yeah?
Yeah, I'll make it work. All right. That was 2/3 of my presentation, so I think we're getting there. But thanks for the heads up. Okay, so now that we covered the basics, now I want to talk, of course, about our technical solution, about what Waygate Technologies is offering and how we are doing that. And now I want to talk about the Phoenix Vitamax M system. It's a very sophisticated, very versatile CT scanner that you can get with a 300 kV tube or with a 240 kV tube, a directional tube, and on top of that with a 180 kV nanofocus source. So it's a dual tube configuration if you want. You can see here some specifications of the system. If you're interested in that, there's much more, of course, on our webpage, or reach out to us and we can give you the full spec sheet of this system. Important for us here in this presentation is it is available as a metrology edition. So you can buy the CT scanner or as a standard CT scanner, and if you want, you can say, well, and also I want it to be a metrology edition. So I want to use that for highly accurate and highly repeatable CT measurements. And if you do that, what do we do? And I want to show you what do we do to make it a metrology edition. So, and of course, the goal is always to have a high accuracy. In the end, it's to have a consistent and accurate voxel size. That's all that matters for us. We want to make sure that if you have a voxel size of 20.795 micrometers, that's exactly what it is. There's no deviation, and each voxel has the same size. That's also important. So, and how do we do that? This is what I want to cover in the last minutes of my presentation. Well, we do a lot. We do a lot of additional things with the machine, but I picked out the three that I think are the most important ones, and they have the most impact, and also are the most interesting ones for this presentation. So, and with a CT scanner, they are kind of always look the same. You have some sort of detector, like in this case, flat panel detector down here. You have some sort of CNC stage, some rotating table that is able to move up, down, left, right, back, forth. And you have one or two or even more X-ray sources here on the right-hand side, so X-ray tubes. And as you can see here, everything is marked red. So everything has its own issues, let's say, when it comes to metrology. These systems work fine and work perfect for many, many years for standard CT analytical scans. But if you want to do metrology on a very high level, so with a very, very high accuracy, keep in mind that I said you have to choose the right equipment for your application. And if your application means we want to have the highest accuracy, then we have to take care of these issues here. And the first one is our detector. So let's talk about our detector for a bit. Our detector is a flat panel detector, our own built in our GE factories in the USA. And when these flat panel detectors come out of the factory, they are not flat. They look flat and they are flat on a certain level, but we are talking again about a few microns here. So really, I think a human hair is something like 80 microns, and this is way too much for us. So we need something like 100th of a human hair diameter. So really, really, really tiny unflatness of this detector. But this is something that is bothering us. Why is that? Because first of all, every detector is different when it comes out of the factory. It's just, again, nothing in the world is perfect. And what does that mean? If we have a, let's call it bended or slightly non-flat detector, each and every pixel has a different magnification because one of the pixels might be in the corner, bended backwards, is a little bit further away from our source than the one in the middle. So we're giving us a different magnification for each and every pixel. That means a different voxel size for each and every pixel. So we don't want that. And what do? Well, we came up with a sophisticated and now patented a way of measuring this surface, this unevenness of the surface. And the thing always is, if we have measured it, if we know it, we can correct it and compensate for it. So each and every pixel, we know exactly how big the offset of this pixel is, and then we can correct it, and then everything is virtually flat, let's call it. So we have a procedure in place that we do in our factory with each and every detector to make sure that we know the unevenness and we compensate it. So that's what we do with our detectors. So one green, two reds to go. Next one is our manipulator, our CNC table. So we are able to move this rotation stage around the whole system. So up, down, left, right, back and forth. And of course, again, nothing is perfect. So if we move, we might not move in a perfectly straight line, although we are using very high accuracy hardware. There's always a limit to what you can do with hardware. So we're moving back and forth, and we might move from position 100 to position 200, but actually we are at position 199.995 without noticing it, right? So what happens? We are at the wrong position. We have a wrong magnification. We have a wrong voxel size. See, it's always about the voxel size. Again, we have a wrong magnification, wrong voxel size. And of course, this is something that we do not want. So, and pretty similar to what we did with the detector, what do? Well, we measure it. We have, again, a very sophisticated procedure on measuring the remaining errors of the axis, and we can compensate these errors. So again, everything, we don't have a problem with inaccuracy. We have a problem with inaccuracy that we don't know. If we know it, we can compensate it. So this is now the CNC side of things, so the axis. And now, now I'm coming to the last bit. So we have now our detectors now virtually flat. Our axes are moving virtually at least straight. So we know where they are. We know exactly where we are. And these two things, that is what we do in the factory. So you as a customer, you don't have to worry about that. You get a machine that's calibrated and everything is working as it should. The last thing is our X-ray tube. Or more precisely, it is the focal spot position from our diagram before. Where is the X-ray created? Well, it's kind of difficult to say. It's somewhere inside the tube, right? You the tube head here, and somewhere inside this solid material, there's somewhere a place where the X-ray is emitted. So no way of measuring it directly with a meter stick or with whatever. And also the other problem is it's not only somewhere where we can't reach it, it's also may move over time. It might change over time, the position, because, for example, if you have a dual tube configuration that we have here, you're able to move your tube up and down and back and forth. And if you move it down and up again, this position might not be exactly at the same position as it was before. Again, we're talking about a few microns here, and everything mechanical moved has its limits. So it might not be at the exact same position. And now there's two things we can do. We can either say, well, okay, every time you move your tube, we send you our service technician and he will fix it for you. That's just not feasible. It takes maybe, depending on where you are, hours or days until you can reuse your system for metrology purpose. So what we came up with is a very easy solution for you as a customer to do your own calibration. So we have a known phantom called the Ruby plate. After you, for example, switched your tube, you just put in the Ruby plate into the CT scanner, click one button, it's doing a calibration with a known phantom, and therefore calibrating exactly the right focus spot distance. So we know after this calibration procedure, we know exactly the scale of the system, we know exactly the voxel size. And then luckily, by the end of my presentation, just in time, everything is green. So now we fixed all the issues with our CT scanner. Now it's a perfect metrology CT scanner. And with all this technology that I've shown you in a very rough overview here, we are able to achieve an accuracy of 3.8 microns plus L being the length you want to measure divided by 100. And again, regarding to this VDI standard. So this is our specification for the Vitamax M Metrology Edition 2.0. So you can see here now we did a lot of measurements between different spheres, the distances, and all these distances are within this 3.8 microns. So no deviation bigger than 3.8. Actually, it's a lot smaller than that. It's around, in this diagram here, it's around 2.5. So with that, I think more or less just on time, I will be giving it back to Jan, and we'll start with a Q&A.